So I'm going to talk about our climate change destabilization problem from a paleohistorical perspective. I have some slides on this, but I also want to integrate some things that have come up this morning so far, which I've noticed. I think that our problem is very urgent and that we need to distinguish between direct, effective, near-term negative emissions technologies and proposals which will have a long-term ecological benefit and which are necessary for us to do, but won't result in near-term carbon drawdown. So I'm concerned with finding examples from paleontology of events that have led to near-term, well, to mass carbon drawdown. And we need to replicate these and speed them up. So you can move to the next one. Yes. So throughout most of Earth history, average atmospheric CO2 concentration has been much higher than it is now. Back in the Pliocene, which was the last time that it reached above 400 parts per million, which is where we are now, the average sea level was about 25 meters higher at a low estimate, possibly up to 50 meters higher. Now, that is due to the concentration of CO2 that is currently in the atmosphere. That is not based on a projection of a future concentration. So we already have a lot of baked-in warming. This also questions the supposition that there is some equilibrium concentration of CO2 that the atmosphere will return to if we entirely cease emissions. So all technologies that rely on emissions reduction without mass drawdown and quickly do not address this issue. Now, calculations of residence time of CO2 are also problematic.
What is the year frame? Like, what is that paleo time frame?
Oh, the Pliocene is about 5 million years ago.
5
million.
Yeah. Is that the era of the dinosaurs?
No, the dinosaurs are about 65 million years ago, so it's much more recent than that. We're talking like early hominids, that kind of thing. So our ancestors would have seen this. But yeah, I can talk more at the end about that, definitely. So these are just some consensus projections of the equilibrium that will eventually be reached in the atmosphere. There's a huge difference between near-term reduction and full geological elimination. Now, I would argue that the second graph here is problematic and is too optimistic, you could say. These are the kinds of projections that the Paris Agreement and, oh, thank you, that the Paris Agreement and other policy-based frameworks are relying on. So we can go to the next slide, actually, yeah. Okay, so this is actually ocean acidification, all right. So, yeah, so policy-based climate solutions or projections rely on arbitrarily defined residence time. Now, as Tom was saying, a large portion of the CO2 that we have released has dissolved into the oceans. And this is why the concentrations haven't risen much higher than they already have. I would say that I think that Tom was saying that otherwise we would be up above 500 parts per million right now. In the Eocene, the concentration was above 1,000. It was possibly 2,000. So we can see that our recent climate is unusual. It has been unusually cold for the past 5 million years compared with the long-term history of the Earth. So this is just a diagram of how CO2 dissolves into the ocean through the physical process rather than biological sequestration of carbon in the ocean. These two are important to distinguish. So what happens, the reason that shells dissolve when the ocean acidifies is that carbonic acid lowers the pH of the ocean and makes it more difficult for shelled animals to retain their shells. What is sometimes neglected here is a concept of carbonate compensation depth, where there is actually a specific depth below which it is impossible to retain a calcareous skeleton. So the problem is not just the long-term pH reduction of the ocean, it is also the changing ecology of the ocean when that raises above the continental shelf, and then you start having ecological devastation up closer to the surface. I don't know how much time I have, but this is a diagram of how carbonate compensation depth works. And if you say that this is a... 5 minutes? Okay, good. So this is a model of where the continental shelf would be, and the problem is greater than simply the overall ocean pH. So if we look at a graph of temperature against CO2 concentration over long-term history, we can see that this would be 4,000 parts per million, this is 1,000, and we are currently about here, right? So we're about 400. Now, if we go across here, we can see that for most of history, CO2 concentration has been significantly higher than it is now. We can also see that the temperature now is very low. The temperature in the mid-Mesozoic went down, but not nearly where it is now, and that the largest ice age in history happened in between the Carbonifera's and Permian periods about 300 million years ago. Throughout history, the warming events that have raised CO2 have happened because of mass addition of CO2 to the atmosphere from volcanic eruptions, and drawdown has happened because of the response of the biosphere to those additions. We are reversing that process right now because we are excavating sequestrated biomass and burning it. So this ice age here, the Permian Carboniferous Ice Age, happened when trees evolved and nothing could digest lignin. It's pretty simple. This temperature decline here in the mid-Eocene happened for a very specific and contingent reason. So this is a diagram of the Permian mass extinction mechanism, which I don't think I have time to talk about right now. So actually move on to the second traps will do, that's better. Okay, so this would be a flood basalt eruption happening here, and then you have a mass addition of CO2 into the atmosphere coupled with aerosols. The aerosols remain in for a shorter period, the carbon remains for longer. You get a whiplash effect where you have an initial cooling followed by a large degree of warming. And this is what generates the whiplash effect on the biosphere and contributes to mass extinction. This is a projection of the interaction between the meteor impact and then the eruptions in India in the Cretaceous tertiary extinction. So we have right now for negative emissions technologies candidates. The mainstream ones are bioenergy with carbon capture and storage, or BECCS, direct air capture, solar radiation management approaches, which would include aerosol injection into the atmosphere, or cloud brightening, or space mirrors, these kinds of things. And another one that I want to talk about quickly at the end is oceanic ion fertilization. So this is the mechanism that caused the initial cooling that has culminated in the ice age that we are in now. And it is amazingly contingent. It is amazing how this process could very easily not have happened. So what occurred was that in the early Eocene, the Arctic Ocean became isolated from the rest of the global marine circulation. It became isolated through continental movement, and many rivers flowed into it. It then developed a freshwater layer on top. The freshwater layer, there were no ice caps. It was warm enough that there were no ice caps. The freshwater layer then enabled a fern called a zolla to grow over the entire surface of the Arctic Ocean. A zolla can fix nitrogen, so it could take that straight from the atmosphere, and so it was able to proliferate over the entire ocean surface. When the azolla died, the layer underneath was anoxic because there was a separation between the fresh and saltwater layers. So it did not rot aerobically, it sunk down and was sequestered. This is the oil and gas in the Arctic National Wildlife Refuge. It is compacted Eocene azolla, the same way that most of the coal deposits that we are burning are carboniferous forests, similarly. So we are now putting back in all of this carbon that went out then. You can move to the next one, actually. Oh yeah, so this is a diagram of the Ozola deposits and how we have these compacted layers of ferns. Sometimes they're 80 meters deep. This whole process happened over a period of about 50,000 years, which geologically is pretty fast, right? So, and we managed, well, the process managed to reduce the atmospheric CO2 concentration from above 2,000 parts per million down to levels about twice what they are now within a period of millennia. So a fern growing in the Arctic Ocean completely changed global climate in a geological instant. This looks like a good idea if we can replicate something like this. Yeah, so this was the best one I could find to illustrate this, and it happens to be in Spanish, but that is fine. This would be in the Carboniferous period. Similar mechanism, bigger issue, went on longer. So about 300 million years ago, trees evolved. When trees evolved, nothing could digest lignin. Lignin was a novel compound, a novel polymer. It contained a lot of cross-linkages. It was very hard to biologically digest. When that happened, that carbon was sequestered and just hung around and didn't rot as biomass just building up on the land. This caused an ice age that went on for about 60 million years before fungi evolved a method of digesting lignin, which is actually much harder to digest energetically than plastic is. So if something is able to digest plastic, that will probably happen pretty soon compared with how long this process took. And I like to say that trees were the plastic of their age because they represented a concentrated, sequestered carbon compound that just lay around, right? What is soon? I would say if it just happened on its own, it's already happening. I would say about 100 years for major degrees of plastic degradation, which will be fun because then plastic objects outside will rot, which will be very weird for us to see, right? Yeah. But in any case, yes, that's how the Carboniferous Ice Age was initiated. There was another event when photosynthesis first evolved called Snowball Earth, when the entire Earth froze solid all the way to the equator. Fluctuations in climate are not new. The equilibrium climate for the Earth is no ice caps and polar temperatures about what they are right now in southern Canada or northern United States, about that. Throughout the whole dinosaur period, which was over 100 million years, nearly 200 million years, that there was no ice. And so there's been ice maybe for about 15% of the history of the Earth. This means that ice-free is the equilibrium state, and that it would be extremely easy for us to perturb the system to the point that we have mass ice collapse and it's very hard to get it back. We want to prevent this from happening, so we need near-term drawdown. So in terms of near-term drawdown, our main candidates right now are direct air capture, sucking CO2 from the air and sequestering it somehow, the bioenergy with carbon capture and storage, solar radiation management approaches, and I will add oceanic ion fertilization, which I think is preferable to those three. And I also think that with improvements in photosynthesis, which could be initiated through nanotechnological approaches, we would be able to generate an analog of that which reduced the CO2 concentration through some kind of very efficient photosynthetic process, and that was what I think that we should do. The oceanographer John Martin said, "Give me half a tanker of iron and I'll give you an ice age," in the 80s. This is because iron is a limiting nutrient in most oceans, in most pelagic environments. So when you have a limiting factor, you can add that one factor and then you will have a massive effect on the proliferation of an organism, right? The problem isn't a lack of nitrogen, the problem isn't a lack of carbon access, the problem is a lack of iron. And so adding finely micronized iron sulfate causes big algal blooms. So this is one of the historical mechanisms of iron fertilization. This is an Aeolian dust plume. This is sand that has blown off the Sahara Desert and is blowing across the Atlantic. These have been declining recently. We don't know why. One would think maybe that with desertification you would get more, but that isn't happening. It may have something to do with wind patterns. The other mechanism of addition is aerosols settling out from volcanic eruptions and dust. So this also is responsible in large part for the fertility of the Amazon, because these go all the way across the Atlantic and they drop iron-rich dust on the rainforest. Go to the next one. Thanks. Okay, so that's another illustration of iron-rich dust going across the Atlantic. Actually, one more. Okay. So these here are algal blooms that were caused by a volcanic eruption in Alaska in 2008. So these are visible from space, and this represents a vast quantity of carbon. Now, in order to make sure this is sequestered, what you have to do is make sure that it sinks efficiently and quickly and doesn't rot aerobically, because then, then you have no sequestration. There have been experiments in iron fertilization that have shown a production of about 100,000 tons of algae per ton of added iron, which would translate, if you have efficiency losses along the system, of about 10,000 tons of carbon. This is pretty good. Now, of course, we can't offset all current emissions with this, maybe 20%, something like that. And we will need multiple approaches to achieve this. This is an illustration of a project called Project Low-Effects in the Southern Ocean, which shows the experimental addition of iron. So, what are some, let's see, so I've just been through pretty quickly a bunch of approaches that with a historical perspective would be useful to think about and could be developed. I think that we have societal problems. We have a problem of a dependence on policy and a fixation on austerity and emissions reduction that is inhibiting our ability to engage in large-scale negative emissions technologies. I know that we need to do it soon, and I hope that all of us here can help come up with processes for doing that leverage all of our different skill sets. My skill set is in the history of the interactions between the biosphere and the Earth system. So if I can help on that level, I want to help. I also think that there are issues with our ethical systems that do not recognize the importance of processes that generate increasing complexity in dissipation of energy. That we do not recognize a life-promoting system of ethics, and that's another thing which I talk about in the article, which I don't think I have time to talk about now. So this is all dependent on ocean circulation patterns. The Southern Ocean is probably the best place to do it because you have the most long-term downwelling, and the circumpolar current helps stop the water coming back up again. You have to not do it in near coastal areas because there's a possible production of toxic metabolites with some diatoms. So there are a whole set of considerations that need to be worked out here. I view solar radiation management approaches as dangerous because they do not deal with ocean acidification, and by reducing the warming, they mask an issue and they reduce societal motivation to deal with it. This is a problem. So this is what I'm worried about. I'm worried that things will get bad, we'll do aerosol injection into the upper atmosphere, and things will continue to degrade, but the temperature won't increase, and so there won't be as much will societally, which I think we need.
All right, thank you.
Thank you.
Okay, I do want to say, I can't believe that you managed to boil down this really impressive document that you wrote in this short talk, but you actually covered a lot of it very quickly. But yes. I do encourage you, go seek him out and read the whole document. It was really, really worth a read.